In this lesson, we are going to take a look at molecules from a quantum mechanical perspective. As you may recall, quantum mechanics is a currently accepted way to describe atoms and molecules. We said that if there's any information you want from atoms and molecules, all you have to do is solve for what's called the wave function. It has all the accessible information about the atom or molecule. What we do is we perform mathematical operations on that wave function to get the information we need. Okay, and we talked about that when we dealt with atoms. These wave functions are determined by solving what's known as the Schrodinger equation. And so when you solve this Schrodinger equation, you get a series of wave functions that are allowed for a given atom or molecule. And so each one of those wave functions corresponds to what we would call an allowed state. Okay, an allowed state is characterized by a well-defined energy. Now, an atomic orbital, when we were talking about atoms, we said that an atomic orbital is just a wave function that describes the state of one electron. And when we talked about atoms with more than one electron, we used what's called the orbital approximation, where we describe the electronic state of the atom, the electronic structure of the atom, by assigning electrons to atomic orbitals. We do the same thing for molecules, and in this case, we define a molecular orbital. Okay, a molecular orbital, just like an atomic orbital, is a mathematical function that gives us information about an electron. Now, for convenience, when we're doing molecular orbitals, we try to express it in terms of atomic orbitals. That just helps us visualize how the atom, how the electrons distribution in a molecule is related to the way they are distributed in the atoms. Okay, so there are two major approaches for constructing molecular orbitals from atomic orbitals. One is known as valence bond theory, and in valence bond theory, the molecular orbitals that we construct describe electrons as shared electrons in terms of overlapping atomic orbitals of neighboring atoms. In other words, we think about bonding as having occurred when you have atomic orbitals of neighboring atoms constructively interfering in the region between them. So we say overlapping atomic orbitals gives rise to bonding. So valence bond theory, the orbitals we say are localized. That means the molecular orbitals are defined in the regions between pairs of atoms. The LCAO-MO theory, which is also just known as the MO theory, refers to the linear combination of atomic orbitals as a way of constructing molecular orbitals. Okay, linear combination is just a process of adding functions so that when we do that for atomic orbitals, we can construct a molecular orbital. It's similar to valence bond theory, except that in the case of LCAO-MO, okay, we express the molecular orbitals in terms of atomic orbitals from all the atoms in the molecule. In other words, a molecular orbital in the MO theory is usually delocalized throughout the entire molecule. It's not just defined in the regions between pairs of atoms. Okay, so let's take a closer look at valence bond theory. In valence bond theory, remember we said that bonding is explained as due to overlapping of atomic orbitals between two nuclei, the two atoms. And when the overlapping of these atomic orbitals lead to a high electron density along the line of centers between the two nuclei. For example, imagine you have two hydrogen atoms. If you have a 1s orbital from this hydrogen and a 1s orbital from this hydrogen, and if they are in phase, in other words, where they overlap, they both have the same algebraic sign, then you get what's called positive interference, constructive interference, and so you get a high electron density between the two. And so that explains bonding between the two hydrogen atoms, and so we say we classify that bonding as sigma bonding. So bonding along the line of centers of two atoms is called a sigma bond. So we say this is a 1s to 1s overlap, this particular sigma bond between two hydrogen atoms in an H2 molecule. Now, in some atoms, you can have some pairs of atoms can have double bonds and triple bonds, as we've seen when we drew Lewis structures. Now, the second and the third bond, okay, are said to be due to pi bonds. So the first bond is always due to the sigma bond. That's the bond along the line of center. You can have a region of high electron density above and below your neighboring atoms, and that would be what? A pi bond. Okay. A second pi bond can be a region of high density in front of and behind. Okay, if you look at these as your two atoms right here, this one and this one. Okay, so if you have two atoms here, okay, a second pi bond would consist of regions of high electron density. Imagine one in front of this pair of atoms and one behind the atoms. Okay, so those are your pi bonds. That would explain the second and the third bond in your pi, or in your triple double bond and your triple bond. Okay, let's just summarize what we have with this example. How many sigma and pi bonds are between the carbon and the nitrogen in HCN? Well, there's a triple bond here. So the first bond between them is a sigma bond. So you have one sigma bond, okay? And you have two pi bonds. The second and the third bond in a triple bond are pi bonds. And we can say that that would be due to overlapping p orbitals in the neighboring atoms. So you have, for example, if this was your z-axis right here, okay, then your pi bond would be due to px orbitals overlapping, okay, and py orbitals overlapping. Okay, so that gives you two pi bonds. And then you have a bond between the carbon and the nitrogen that's called a sigma bond, the first bond. Valence bond theory is particularly useful in explaining molecular geometry. And to do this, we use a concept known as orbital hybridization. Let's illustrate that with this example right here, acetylene, okay, C2H2. This is the Lewis structure for acetylene. You have a triple bond between the two carbon atoms, and each carbon atom is a single bond with a hydrogen. Now, so the sigma bond, the first bond between these two carbon atoms, okay, is a sigma bond, and then the two other bonds would be a pi bond. So because the shape, we predicted the shape of this molecule, and experimental observations corroborate that prediction, that this HCH angle is 180 degrees. Okay, that means this sigma bond between these two carbon atoms and this sigma bond between the carbon and the hydrogen atom are oriented 180 degrees apart. Okay, so how do we explain that? Well, first of all, the second and the third bond between these two carbon atoms, we said, if you remember, we said earlier, is due to pi bonding, right? So we say it's due to overlap between neighboring p orbitals. So you might have a px orbital on this carbon and a px orbital on this other carbon. The overlapping of those two gives rise to one of the two pi bonds. The other pi bond comes about when you have an overlap between the py orbital on this carbon and the py orbital on the other carbon. Okay, so that takes care of the two pi bonds. So in other words, we're assuming here that this is our z-axis, okay, and then your x-axis would be this way, and your y-axis would be this way. All right, so now let's explain the sigma bonds. Why are those sigma bonds 180 degrees apart? The way you explain it is this. Okay, think about the carbon atom. A free carbon atom, we said, in its valence subshell, okay, in valence shell, has a 2s and a 2p subshell, right? So 1s2, 2s2, 2p2. It has 4 electrons in the valence shell. Okay, so if we draw the orbital diagram, you would have something like this: 1s, 2s, 2p. Remember, 2p subshell consists of 3 orbitals, and so you have 2 electrons in the 1s, 2 electrons in the 2s, and then 2 electrons in the 2p orbital. Okay. Only the valence orbitals are going to be involved in bonding, right? The inner electrons are not involved in bonding. So you've got 4 electrons in a valence shell, but only 2 of those are unpaired. So how can carbon end up having 4 pairs in a molecule? Then we try to explain that by saying, okay, it must be that before the bonds are formed, one of these electrons in the 2s must have transferred over to the 2p. Okay? So what happens then? Well, so we say now our orbital diagram for the carbon atom in the molecule would now be, for the valence shell, would have 1 electron in the 2s and 1 electron in each of the 2p orbitals. Okay? And we say we can take into account, okay, 2 of the pairs as being due to involving the 2px and the 2py. So the 2 other pairs that the carbon must be using for a sigma bond must be the 2s and the 2pz orbital. Okay? So the explanation for the 180-degree angle between the two sigma bonds is as follows. You say that this 2s and this 2p orbital no longer exist in the molecule. Okay, so instead of having a 2s, 2pz, 2px, and 2py, okay, in the molecule, the carbon atom now has a pair of hybrid orbitals. Okay, it uses a hybrid of the s and the 2s and the 2pz orbital to create for bonding with other atoms in this particular case. So what we're saying then is, okay, so here's, remember an s orbital is spherically symmetrical, right? And a 2pz orbital, if this is your z-axis right here, would be positive on one side and negative on the other side, right? So let's just say it is positive on this side. Let me color code this. Let me do this again. All right, so let's say the 1s is positive. All right, so the 2pz orbital is positive on one side, negative on the other side. Okay, so we say that instead of a 2pz and a 2s orbital, what you end up having in the molecule are 2 hybrids. So when you have when you add these 2, okay, then what ends up happening is when you add this 2s and the 2pz orbital, what ends up happening is that on this side of the nucleus, on this side, on the left side, you have destructive interference. So the resulting hybrid orbital would have a very low amplitude on one side of the atom, and these the positives would reinforce on the other side. On this side right here, you have positive reinforcements. You have constructive interference here. Constructive interference of the wave functions. So you have a high density, high probability of finding the electron there now. And then the other possible hybridization is one where you subtract. So now if you subtract, so this essentially becomes positive and the other side becomes negative. So your hybrid orbital will now have a high electron density on one side as opposed to the other side. Now these 2 hybrid orbitals would be directed 180 degrees apart. Okay, so we then say that one of these hybrid orbitals, the one that's pointing to the left, is going to overlap with the 1s orbital of hydrogen. So if I have a 1s orbital from hydrogen right here, and we have the sp orbital from the carbon, yeah, that overlap gives rise to one of the 2 sigma bonds, this CH bond right here. So we say that this is an S to sp overlap. Okay, S to sp overlap. The s orbital of a hydrogen overlaps with an sp hybrid from carbon. That accounts for that sigma bond. And the other sigma bond right here is an sp orbital of this carbon right here overlaps with the sp orbital of this other carbon right here. So this other carbon also undergoes sp hybridization in this particular molecule. So that's how you would explain the bonding in acetylene using valence bond theory. Okay. In general, we can explain the electron domain geometry that we predict using VSEPR by invoking the following hybridization schemes. Okay, so for steric number of 2, as we've seen earlier, we have to invoke an sp hybridization. So if you hybridize an s orbital and a p orbital, that gives you 2 hybrid orbitals, and those are all sp, or both of those are sp orbitals that are going to be directed 180 degrees apart. Okay, so that would explain the linear geometry around a central atom that has 2 groups of electrons sticking out of it. So the 2 sigma bonds that will come that atom will be forming will be using an sp hybrid to overlap with the neighboring atom. If the steric number is 3, then in order to get that 120 degree bond angles of the sigma bonds sticking out of the atom, you're going to need an sp2 hybridization. That means you have to hybridize an s orbital with 2 of the p orbitals, and that will give you 3 hybrid orbitals, and those hybrid orbitals, we call them sp2 hybrids. And similarly, if you want to account for the tetrahedral arrangement of 4 electron domains sticking out of an atom, then you're going to have to hybridize an s orbital with 3 p orbitals. Okay, and that should give you 4 sp3 hybrids. So each of these orbitals, for example, in methane, okay, CH4, if you remember, that's a tetrahedral structure. The geometry is tetrahedral. You have 4 groups. Okay, 4. So you have 4 single bonds sticking out of your carbon atom. So you have 4 sigma bonds there. 4 CH bonds. Each one of those is a sigma bond. The hybridization, the hybridized orbital that your carbon atom is using to create those sigma bonds is an sp3 hybrid. Okay, so the hybrid, each of those 4 bonds uses an sp3 hybrid from the carbon atom. For steric number 5, you recall, to get, if you have a steric number of 5, you'll have to invoke, the geometry is trigonal bipyramidal. You have three pairs of three electron domains oriented 120 degrees apart, right? Sorry, 120 degrees apart, and then those are your equatorial groups, and then you have 2 axial groups. You can imagine those as pointing towards the North Pole and the South Pole. So here's your axial group. This is an axial group down here, and you have 3 equatorial groups. For that, you're going to need to hybridize 5 orbitals, and those 5 orbitals are an s orbital, 3 p orbitals, and a d orbital. Okay, and so remember we said before that if you have atoms in row number 3 or below, they can have more than an octet. This is one case where you can have an atom having more than an octet. In this case, you can have like 10 electrons around, 10 valence electrons around the atom. And the reason it can do that is because you can now avail of those available p orbitals. So we hybridize one of the d orbitals with an s and the 3 p orbitals. That will allow you to get 5 hybrid orbitals, and we call those hybrid orbitals sp3d. And finally, if you have a steric number of 6, you're going to need to hybridize an s orbital, 3 p orbitals, and 2 d orbitals. So the hybridization is sp3d2. Okay, so let's apply those to this question right here. According to valence bond method, what hybrid orbitals would be involved in the overlap what hybrid orbitals will overlap between the carbon and nitrogen in this structure for urea? So this is urea. So this carbon to nitrogen bond, what would be the hybrid orbitals involved in the overlap? Let's take a look at carbon. Carbon, as the steric number for carbon is 3, right? There's 3 groups sticking out of the carbon, so we know that this should be 120 degrees, that should be 120 degrees, and that should be 120 degrees. 3 groups sticking out of the carbon atom should be at 120 degrees apart. So the hybridization you're going to need here is sp2. So the carbon will have to use an sp2, and it's going to overlap with what hybrid for nitrogen? Look at nitrogen right here. There's 1, 2, 3, 4. 4 groups of electrons sticking out of your nitrogen. So the steric number for your nitrogen is 4. That's a tetrahedral electron domain geometry. So the hybridization that you're going to need for the nitrogen is an sp3. Okay? So we say that the carbon to nitrogen bond here is an sp2 to sp3 overlap. Okay, we can also use valence bond theory and orbital hybridization to explain bond lengths. Generally, if you have hybrid orbitals that have a greater p character, they tend to stretch further out from the nucleus, and that would lead to a longer bond length. So, for example, if you have a carbon sp2 hybrid, okay, it's going to stretch out farther than an sp hybrid, and an sp3 hybrid is going to stretch out further away from your carbon atom. So that could lead to longer bonds. If you have to compare two cases where in one case carbon uses sp3 for bonding and in another case it's using sp2, you would expect the bond involving sp3 to be longer, provided the other side is the same. Okay, the other side of the bond is the same. So here's an example. Let's compare C2, this is ethane right here, and ethane, and this is ethylene or ethene. And the difference between these two is that this is a single bond here and this is a double bond. So this is CH3, the bond, and this is CH2, double bond, CH2. Okay? So how do we explain the differences in the bond lengths here? What do you notice about this single carbon-carbon single bond? It says here that the bond length is 153.1 picometers, whereas over here for the double bond, carbon-carbon double bond, your bond length is 133.9. So the carbon-carbon double bond is shorter than the carbon-carbon single bond. Why is that? Well, can explain that using the notion of hybridization by saying that, okay, this carbon right here, this is 1, has a steric number of 4, right? So it's 1, 2, 3, 4 groups sticking out of it. So this carbon here is an sp3, and this carbon is also sp3, using sp3 for signal bonding. So you're looking at an sp3 to sp3 overlap in ethane, okay? Whereas in ethylene, your overlap is sp2. This carbon has 1, 2, 3 groups sticking out of it. So this is an sp2, and this carbon also has 3 groups sticking out of it. So that's an sp2 to sp2 overlap. And so we said this sp3 orbital, this sp3 hybrid has greater p character. So the electron density around that carbon is going to stretch out farther away than the electron density around this carbon in an sp2 hybrid. So you expect this single bond to be longer than the double bond. Now let's compare the carbon to hydrogen bonds. If you look at the bond between carbon and hydrogen, all right, this bond right here is 109.4 picometers. Carbon to hydrogen, but this carbon to hydrogen is 108, and again this length right here is shorter. How do we explain that? Okay, so hydrogen to carbon bond here is S to sp3 overlap, whereas the hydrogen to carbon bond here is an S to sp2 overlap. And again, because the carbon here on the right is using hybrid orbital with lower p character, less p character, sp2, we expect that bond to be shorter. There's a couple of excellent animations on the web that you really should take a look. These animations explain hybridization really well as sigma and pi bonding. I put those links in the internet resources section for this topic, molecular structure, on our Moodle website. Okay, so this link right here takes you to that animation for that explains hybridization, and this second link over here takes you to the animation that explains sigma and pi bonding. Or you can just go search for it. So if you go to Google, just search animation, just type the word animation orbital hybridization, and it's probably the first link that will show up on your search. It's one of the best ones out there. So if you click on this hybridization right here, it will take you to that
in the 1930s,
website. Okay.
Introduced the concept of hybridization to explain chemical bond formation.
And then if you do a search for animation, sigma and pi bonds, okay, that other animation will be the first one you'll probably see on Google. And so if you click on that, it will
Let's
show
examine the bonding in three molecules, ethane, ethylene.
So it will show you how sigma and pi bonding happens in ethane, ethylene, and acetylene. Okay, it explains it in terms of hybridization and overlap of atomic orbitals. Okay. All right. So now let's take a look at the LCAO-MO theory. Okay. As we said earlier, in this particular approach, you construct molecular orbitals by combining atomic orbitals from all the atoms in the molecule. Now, not every atomic orbital is going to contribute to a particular molecular orbital. Okay. So contributions of your atomic orbitals to a particular MO are not going to be equal. They will depend on the symmetry of the molecule. For example, the 6 p orbitals of the 6 carbons in benzene. Benzene is C6H6. Okay. Each of those carbon atoms has a 2p orbital that can contribute to 6 of possible pi molecular orbitals. Okay, so there are molecular orbitals called that involve delocalization of electrons around the benzene ring. Okay, and these are the 6 orbitals you can get, 6 molecular orbitals. They're labeled psi1, psi2. You have 2 psi2 orbitals that have they're different, but they have the same energy, and then psi3 refers to the 3rd energy level, the orbitals for the 3rd energy level. So these are your molecular orbitals as they are constructed from the p orbitals of the 6 carbon atoms. Okay. Now, in comparison to the energy of the p orbitals where they come from, it turns out that these 3, okay, molecular orbitals are lower in energy. So this dashed line right here in this diagram represents the energy level of the 6 p orbitals of the 6 carbon atoms. And so any molecular orbital that you form that would be lower in energy than the atomic orbitals themselves would be what we would call a bonding orbital. So if by forming those orbitals we say a molecule has achieved some kind of stability, and these orbitals up here that are higher in energy than the atomic orbitals that they come from are known as the anti-bonding orbitals. Okay. So a molecular orbital diagram summarizes how the molecular orbitals are related to the atomic orbitals. In other words, tells you where they come from. For example, here this molecular orbital called 1s sigma comes from a combination of the 1s orbitals on 2 atoms. This is for diatomic molecules. So this is a diagram, an orbital diagram for a diatomic molecule. Okay, in particular, a homonuclear diatomic molecule. Homonuclear means same 2 atoms, like H2 or He2 or Li2. Okay, so the 1s orbitals can combine to give you a bonding orbital, which would be lower in energy than either of the atomic orbitals, or they can also give you what's called an anti-bonding orbital. So 1s sigma star, the star in the label for the orbitals indicates anti-bonding. So the 1s sigma star, that's another molecular orbital which happens to have higher energy than than the atomic orbitals that it came from, so that would be called an anti-bonding orbital. Okay, so a molecule that has lower energy than the contributing atomic orbitals are called bonding orbitals. Those that are higher energy are called anti-bonding orbitals. For diatomic molecules, names of molecular orbitals are given by the Greek letters sigma, pi, delta, and phi. It's analogous to S, P, D, and F for atoms. And for molecules, we use sigma, pi, delta, and phi. In this particular case, in this diagram that we have here, this is a sigma. It's called the 1s sigma. This is 1s sigma star. This is 2s sigma. This is 2s sigma star. This is 2p sigma. So the labels tell you what atomic orbitals the molecular orbital came from. So when you say 2s sigma, that's a sigma orbital that's formed between the 2s orbitals. Okay, so this 2p sigma right here means that's a sigma orbital that's formed between two 2p orbitals. So if I have a 2pz orbital this way, okay, which is positive on this side, let's say, and negative on this side, and then another 2pz orbital in the other atom would be over here, positive and negative on the other side, and that gives me a bonding orbital. Okay, that's a sigma orbital between those two atoms. That's constructed from their 2pz orbitals. Now, in general, bonding orbitals are the ones that have the high electron density between, so you have constructive interference of the orbitals between the nuclei, whereas anti-bonding orbitals would give you a molecular orbital that has a node, we say a node. That means between the nuclei. A node simply means that the probability of finding electrons between the nuclei is negligible, is small, so that makes the nuclei see each other better, you might say. So there will be a stronger repulsion. So that's why that's an anti-bonding situation. Okay. If you do an internet search for molecular orbitals, there's a lot of websites that you'll find will give you very nice images to help you visualize how molecular orbitals are constructed from atomic orbitals. So here's a search that I just did. One of the better ones to look at is the one, if you can find one from Purdue University, this one right here, chemed.chem.purdue.edu. So that particular link's pretty nice. Here it shows you how you can construct a bonding orbital from two 1s orbitals. Okay, so if you have a 1s on one atom and a 1s orbital from the other atom, let's call those atoms A and B, you get a sigma bonding orbital right here, sigma 1s. And if you do 1s minus from atom A minus 1s from atom B, then right here in between the nuclei, you'll see destructive interference, so you get a node between them. Okay, so here's a diagram that results from that. Okay. Right here. So the bonding orbital would be lower in energy than the two atomic orbitals, and the anti-bonding orbital would be higher in energy. Okay, so that's the orbital diagram for that. And further down here, here's an illustration of how you can construct a sigma bonding orbital from two pz orbitals. So this is 2pz orbital for atom A, and it's a 2pz orbital for atom B. Okay, so if the positive lobes overlap, you get a bonding orbital. If this lobe was negative, okay, if this lobe was positive and this lobe was negative, you get an anti-bonding orbital, sigma anti-bonding orbital. So again, here you have a node in between the nuclei where there's a low electron density. Okay, and here down here you have a diagram that illustrates how you can get pi orbitals from a pair of 2px orbitals. So you have a 2px orbital on one atom and another 2px orbital from the other atom. So let's call this atom A and atom B. Okay, if they're both positive on the same side and negative on the same side, then you end up with a molecular orbital which is positive on one side and negative on the other side. And so that's going to be a pi bonding orbital. So, and if this was negative, okay, right here, then you would end up with a pi anti-bonding orbital. Now, pi orbitals generally come as a pair, okay, because you can construct a pi orbital using px orbitals and another pi orbital using py orbitals, and those will have the same energy, okay? And same thing with pi star orbitals. You can construct pi star orbitals from px, or a couple of px orbitals, and a pi star orbital from a couple of py orbitals. So what kinds of information can we get from a molecular orbital diagram? You use the molecular orbital diagram to calculate what's called the bond order. And basically a bond order of 1 means that you expect there to be a single bond between the two atoms. A bond of order of 2 means you expect a double bond to form between them, and a bond order of 3 means you expect a triple bond to form between them. So if you get a bond order that's greater than 0, you can predict that there's a stable bond between the atoms. Now, if your bond order is 0, then that means you don't expect that bond to be stable. Okay? How do you calculate the bond order? What you do is you assign electrons to orbitals just like we do for atoms. 2 electrons per orbital, 1 spin up, 1 spin down, okay, maximum of 2. And the bond order would just be the number of electrons in the bonding orbitals minus the number of electrons in the anti-bonding orbitals, and you divide that by 2. So let's illustrate that with this diagram. This is the molecular orbital diagram for a diatomic molecule. So this would be applicable, for example, for F2. F2, if you recall, has 9 electrons times 2. That's 18 electrons. Okay, atomic number of fluorine is 9. It's 1s2, 2s2, 2p5. Okay, 2 electrons in the core and 7 electrons in the valence shell. So let's assign those 18 electrons. We have 1, 2, 3, 4. So 2 in the 1s sigma, 2 in the 1s sigma star, and then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay? Now, if you look at these orbitals, you can say, let's look at the bonding orbitals. This is bonding, this is bonding, this is bonding, this is bonding, that's bonding. So you have 2, 4, 6, 8, 10 electrons in bonding orbitals. And the number of electrons in the anti-bonding orbitals are 1, 2, 4, 6, 8. So 10 minus 8 divided by 2, that gives you 1. The bond order for fluorine is 1, so we expect fluorine to have a single bond. Okay? Let's do the same thing for oxygen. Oops, I don't have oxygen. Let's try oxygen. Okay. What will be the bond order for oxygen? So let's do oxygen. Oxygen would be 16 electrons, right? 8 times 2. 1s2, 2s2, 2p4, right? 6 in the valence shell and 2 in the core for each atom. So 16 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Note that we're spreading out the electrons between the 2 pi orbitals before we pair them off. Okay? So let's look at our bonding electrons in our bonding orbitals. We got 1, 2, 3, 4, 5 pairs. So that's 10 electrons in the bonding orbitals. Okay? Electrons in the anti-bonding orbitals are 2, 4, 5, 6, minus 6. So divided by 2, that gives you a bond order of 2. We expect oxygen to have a double bond. But look, there's something interesting here. Okay? Even though we expect oxygen to have a double bond, look at this two unpaired electrons here. Molecular orbital theory, LCAO-MO theory, predicts that two of the electrons in oxygen are not actually paired. They're in separate pi orbitals. And one experimental evidence that supports this is the fact that oxygen is paramagnetic. It responds to the presence of an external magnet. So that's a property that we associate with unpaired electrons. Okay. Now, if you did nitrogen, you'll find that this nitrogen would have 14 valence electrons. So if you did nitrogen, you'll have 2 less, and so your bond order would end up being 3. What about He2? What would be the bond order for a diatomic helium molecule? Well, helium, if you recall, has 2 electrons. 1s2 is the electron configuration for a helium atom, so He2 would have 2 times 2 or 4 electrons. Okay, so we assign the first 2 electrons in the 1s sigma molecular orbital, which is a bonding orbital, and then the next 2 electrons would be in the anti-bonding 1s sigma star orbital. So you have 2 bonding electrons minus 2 anti-bonding electrons divided by 2. That gives you a bond order of 0. So we don't expect the He2 molecule to be stable according to molecular orbital theory.